Okay, let's get started. Everybody, can you see my screen?
Yes.
Okay, great. You see, today we will start the new chapter, Fourier circuit analysis. So I believe you all have known about the Fourier analysis, probably in the signals and system course as well as in any math course. For this class, we will basically apply the Fourier circuit technique to the circuit problems. So therefore, see that if you have already covered these things. Now, what is the application? In terms of application, you see, as I mentioned, that those are useful in harmonics or frequency spectrum analysis, in filter circuit, in communication, electrical circuits, etc. So this means that uh, for a circuit, you have applied sinusoidal signal or other form of signal, but always signal might not be sinusoidal, or it might look like sinusoidal, but there can be some impurity. There can be some noise or oscillation, which are called as harmonics. And if there is harmonics, then not only the 60 hertz, not only the fundamental frequency, there can be higher order frequency. For example, frequency can be 120 hertz, can be 180 hertz, and higher, even more than 1000, 2000 hertz. But those are unwanted signal. You need only the 60 hertz signal, pure sinusoidal signal. So therefore, Fourier circuit, Fourier technique will help you to find out that fundamental. So that's why it is called the Fourier circuit technique. Now, signal can be periodic, that sinusoidal signal can be periodic or can be non-periodic. Sometimes it is called aperiodic. Accordingly, there are two terms. One is called Fourier series, and other term is called the Fourier transform. So Fourier series means that will handle the periodic function, and Fourier transform means it will deals with non-periodic function. So that is the difference. Now, periodic, non-periodic, whatever it is, if it is not, if it does not look like sinusoidal, there is some oscillation, noise, and then it is appropriate to apply that Fourier technique to find out what is the desired signal. Same thing, as I mentioned in the filter circuit, whatever the filter, high pass, low pass, or band stop, or other active filters, there can be some noise or oscillation, higher order frequency. You have to find out those things, then you can properly apply. That is the meaning or significance of this Fourier circuit analysis technique. Now, you all know, I mean, soon with few example, I will jump to the circuit problems. So here I have written, you all know that if there is any periodic function, for example, this one, then that periodic function having frequency omega naught can be expressed as an infinite sum of sine or cosine function that are integral multiples of omega naught. So this means you have looked in signals course or math course that if there is a function ft and it can be decomposed into several components, a naught plus you see a on cosine of omega naught t plus b on sine of omega naught t. Then for here you see it was cosine of omega naught, the cosine 2, cosine 3, cosine n times. This means if you say this omega naught is fundamental frequency, which is 60 hertz, then 3 is the 3 times of 60. Or if it is n times, then n times of 60. So therefore, as you can see, that this function has been decomposed into several components, but these are all are like cosine, cosine, or the sine. So sine, cosine is not the problem, just 90-degree phase shift that you did. But you see the very first term, A naught. So A naught does not have any cosine or sine term. So what does that mean? This means A naught is the DC component because this is constant value. So this means You are decomposing, you are analyzing a periodic function, and then you are getting all of those terms, both cosine component, sine component, fundamental frequency, higher order frequency, plus DC. Now, for example, you want only this signal. Your target, your desire to get this signal, A1 cosine of omega naught t, because it has that 60 hertz omega naught, like 2 pi f. Therefore, that A naught and then remaining all of those terms are undesired. You don't want those signals. That is the necessity of Fourier circuit analysis. So when you are looking this signal, you don't know that does it include this one or in sine 3 or sine 5t, or does it have A naught? You don't know. And then Fourier circuit technique will help you to decompose, and then you pick up what you need. So everybody, could you follow me what I am talking?
Yes, sir.
Okay, so you all then let's have some example. For example, here you see example of non-linear loads. Think this example, that this is a simple circuit. It has resistance, and I am showing that this is variable resistance. And see, this is my voltage, VT. Everybody see that voltage is purely sinusoidal. It is 100% sinusoidal. There is no noise, no harmonics. But this resistance, you see, I have written its characteristics, voltage versus I. It is not a straight line. It's a nonlinear resistance. So when you are applying this pure sinusoidal, although voltage here is purely sinusoidal, but once current is flowing through this nonlinear resistance, because of this property, you see the response of IT a little bit deviated than this one. Everybody compare these two. This is purely sinusoidal, but this is not purely sinusoidal. Now, if you analyze with the help of Fourier, then probably you might get not only just 60 hertz signal, higher order signal, or even DC. Therefore, in this case, Fourier circuit is applicable. Fourier transform technique is applicable. Everybody see here another example. You look, this is a signal. For example, from this type of circuit, you got this signal. You see, originally your signal, your source was like that, but it is your output, for example. Therefore, it looks like the sinusoidal. There is pattern. It is repeating. It is periodic signal, but unfortunately, there are lots of oscillation and the noise on it. Now, Fourier representation. If you analyze this signal, then you see first one, you are getting pure sinusoidal. I have written 60 hertz. And then there can be this signal. Therefore, this signal plus this, plus this, plus this, there can be higher order components. And if you see gradually the frequency is increasing. This on 180 hertz, this on 300, at 780 hertz, even it could be much higher. Therefore, with the help of Fourier technique, you can get this signal. And then you pick up which one is desired, what you are looking for. Are you looking for this one or this one? So, and then 60 hertz, the age value is 180 because it is 3 times. So age value of 3. H refers to harmonics, harmonic order. Accordingly, this is first order harmonic, third order, fifth order. Accordingly, it goes. So therefore, why we are analyzing this type of signal? Therefore, if you see on real life, like here I mentioned non-linear loads, at your home, at our home, most of the loads is non-linear. That's why I have brought this example in front of you. Therefore, see some realistic example that when we will get this type or this type of waveform, and what is the necessity of having this Fourier circuit technique. Everybody see example of harmonics. For example, I have written here clothes dryer current waveform. You see, not purely sinusoidal. It looks like so there is problem here, a little bit problem here. And then you see a little bit deviated. These all are like deviated and different load. Refrigerator current waveform, conventional heat pump current waveform, stove top plus oven current waveform. And then here there are further example, microwave wave current waveform, a color television, you see color television current waveform, you see hugely deviated. It looks like this and then this is going, and instead of coming in that way, it became like zero, and then again it is coming in that way it is going. So again look, these signals, desktop computer plus laser printer current waveform. So therefore, this represents those harmonics. Therefore, you look, they are periodic signal. They are repeating after a certain time. You see this signal, it is going, and then again it will be like that. So they all are looks like periodic signal and looks like about sinusoidal, not pure sinusoidal. There is harmonics. Harmonics means there is higher order frequency beyond 60 hertz. Therefore, in these cases, you have to apply the Fourier technique. So therefore, these are all the like realistic example. Okay, now moving forward, you all did in either math or in signal system. So briefly, I will tell how to decompose that, and then I will jump into the circuit problems. So I was showing you a few minutes back that function t having its a periodic, but there is noise or oscillation on it, then it can be decomposed in that way. DC component plus AC component, but fundamental frequency and higher order frequency. Now, if I generalized this first equation, the first of all, this pattern is called, because there is sine cosine, trigonometric Fourier series. It is called trigonometric Fourier series. Now, look, the second line, this is generalized format. This is a naught constant term. What here, because there is repetitive pattern like cosine, cosine, just omega 2, cosine 3, similarly sine omega naught, sine 2, sine 3, plus dot 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 sine n. So you can write in that format that summation n on equal to infinity, then in parentheses a n cosine n on omega t for all cosine term. Similarly, for all sine term, you can say this one, that there is constant v subscript n sine n omega t. So this is general format. Now you have a signal ft and you want to decompose with the help of Fourier technique, but you are noticing cosine sine is fine. You know that those are trigonometric function, but n is constant, bn is a constant, and then definitely a naught is also a constant. So how to get that a naught, an, and bn? So if you can find out what is a naught, what is a1, and what is b naught, so after finding, if you plug in equation 1, then you are done. Therefore, in Fourier series technique, what you do, for example, there is a function given ft, and find out its Fourier series representation. Then you just need to find out three constant, a naught, a1, and bn, and then plug in this equation. So that's the result. Whatever the format is, whatever the number of n value is. So therefore, in this generalized equation, omega naught definition, as I said, that is fundamental frequency. So you know omega is 2 pi f, and f is 1 over t. Like t is the time period. And I have written that fundamental frequency in radian per second. And that cosine n omega naught and sine n omega naught in the equation, they are called the nth harmonic of that function, harmonic. And then the procedure to determine a naught, an, and bn, those are called the Fourier analysis. Therefore, Fourier analysis mean Fourier series application means finding out those three constants, a naught, an, and bn. Now, how to find out those three? Here, like I am showing. So I believe you already know, but just one, just a repetition. This is your basic equation. So everybody concentrate on number equation one, this one. What I am doing, I am first finding a naught. That is my target. Integrating both sides of equation on over on time period. So the time period is t, capital T. So over that time period, integrate. So you see left side, I am integrating 0 to t, function of t dt, and then the whole thing I have written in parenthesis dt, 0 to t. And then I am decomposing a0, then dt, plus this term, plus this term. Now I am writing this ft dt left side as it is, and from here you see this term and this term will be 0. Integration of cosine of n omega naught, integration of sine n omega naught, they will give you 0. So therefore, for everybody, you see, in the next two slide, I have written down all function, trigonometric integral, you see, sine n omega naught t dt 0, this 0, this 0. Therefore, when you will be analyzing the Fourier series, you can directly apply these integral or identities. So without doing that one. So similarly, in the next page, I have written all list. If you see this function, then result will be t by 2. If you see cos 2n by, result is 1. Sin 2n by 0. Cos n by minus 1 to the power n. In that way, I have made it available. You can directly look and then you can apply that one without analyzing. So that is the meaning. So in next two slides, I have made available those two trigonometric integrals. So therefore here you see integral 0 to t sine n omega naught t, it is 0. Cosine n omega naught t dt, that is also 0. Accordingly, here I was saying using this function, it will give you 0. This function, it will give you 0. Therefore, only for this term, this is a naught. And you all know that after integration, you will be getting t. And then if you put lower limit, upper limit, you will be getting capital T. So therefore, ultimately, from this two, you are getting a naught is divided by t on over t integration of 0 to 2 ft dt. So therefore, in other words, if you remember average value and then RMS value, when we are discussing, this actually represents the average value of function of t. And that makes sense. Average value of a AC waveform represents the DC. As I said, in fact, this A naught represents the DC signal because this constant voltage or constant current, whatever it is. And this represents the sinusoidal function. Therefore, you have to note down this one, this equation A naught 1 over T integration of 0 to ft dt. This you will need to find out the A naught constant when you are analyzing Fourier series. So therefore, everybody, please just note down the last equation momentarily. Could you follow me, everybody, what I am saying?
Yes.
Yeah. So you all know, I mean, as I said, I believe you already know, just I am refreshing your mind. So you may write down the very last equation, and I would recommend you all, everybody, write down the equation number 1. I mean, soon today we will apply. I will show you example, and then also I will discuss the circuit problem. Everybody, you can note down equation 1, only equation 1, and the last equation. A naught is 1 over t, this one. Just note down the equation on generalized format ft a naught plus summation n on equal to infinity, and then in parenthesis n cosine n omega naught t plus bn sine n omega naught t, and parenthesis close, where omega naught is 2 pi by t. Have you all written down? Please your pen and paper. Just equation 1 you write down, and then last equation. Are you done?
Yes.
Yes.
Okay, yeah. I mean, although I can back and forth, but momentarily. Okay, fine. Now, we calculated A naught, in this equation. Now we will calculate N and Vn, yeah, these two constant. Then we are done. Now, to find out that N, that multiplying both side of equation 1 means again that equation, if you multiply both side by cosine m omega naught t, you multiply by that both sides and then integrate over one time period. So therefore you see, left side you have only the ft, but now I am multiplying by cosine m omega naught t and then integrating over one time period 0 to capital T. Then right side, that previous function multiplied by cosine omega naught t. And then you see, just I am decomposing the terms. And again, you see these things, cosine of n omega naught t, cosine of m omega naught t. You see this function, I have written trigonometric integral. These will be 0 when m not equal to n. Similarly, sine and sine, this will be 0 when m not equal to n. And then this one, sine cosine multiplication, that is also 0. So therefore, if I use these things, then this thing 0, this thing 0, and I am getting when m equal to n, a n t over 2. Therefore, from here, a n value is 2 by t, and then this function. This means this is your result. This is that a n constant value. So therefore, you can note down this one. N equal to 2 over t, integration 0 to t, ft cosine of n omega naught t. And then similarly, for bn, you need to multiply both sides by that sine m omega naught t, then you will be getting this one. Vn is 2 over t, integration of ft sine n omega naught t. So therefore, everybody, you now note down this an value and then bn value. These all are just the calculation and the math, and you will be applying these things. That is fine. So for the problem solving, you don't need to do those. Just you will be directly applying this integral function. But you have to properly write down this function, and then the previous a naught function. Those are needed. So everybody, please write down that an function and bn function. Just you write down this one. N is 2 by t, integration 0 to t, ft cosine of n omega naught t dt, and then v on this one. And then, as I said, you can, you may or may not remember, but you are feel free to look these things when solving problem. Similarly, in the next slide, you see all trigonometric function I have made available in front of you. If you see this function, directly use this one. If you see this function, directly use this one. So that will help you. So have you all noted down an and bn?
Yes.
Okay, great. Yeah. So now I will show you one example how to apply that one, and then I will take you the circuit problem. So everybody see here, find the Fourier series of the following waveform. Therefore, see this one, everybody, this function here function of t in this axis t, here the magnitude 1, and here like 1, t value 1, t value 2, t value 3. Therefore, if you see the pattern, it is like that, and it is 0 here, and then again it is repeating. So this means, what is the time period? Time period is 2. Capital T is 2, because after 2 it is repeating this pattern. So therefore, I have written that on here. First I am writing what is the function value. Function of t is 1 when it is the range between 0 and 1 t value, and then function value is 0 between 1 and 2. That just I indicated. And I am writing that capital T is 2, that I just told you. And I am finding omega naught because that will be needed in the generalized form. You see, this is the generalized form, that equation 1 actually that I showed before. So what is omega naught? 2 pi by t. What is my t? 2. So therefore you see, if I put 2 cancelled, omega naught is your pi. And then then I am done. I am writing that generalized equation first, and then I'm writing a naught, and then an value and bn value. So you may not write these here. You can directly start from here. Just I'm showing one example. That's why I'm writing at first in that way. Now everybody see, first I want to calculate a naught. So this is my equation that I've learned in previous slides. So 1 over t. What is my t? T is 2. Already I find out for this function. 1 by 2. And function of t has two portion. This is one portion and this is other portion. So from 0 to 1, 1, and then 1 to 2, that is 0. So just I am writing in that way. 0 to 1, function value is 1 dt plus between 1 and 2, 0 dt. So you may not write, just here I am showing you like how you have to do, what is the procedure, but you may not write because you clearly know that this will give you 0. Anyway, so therefore this is half, this is 0, but on dt, so you will be getting after integration t, right? And then I am putting the lower limit and upper limit, 0, 1. So if you put that on, ultimately you will be getting just half. So this means a naught value is half. Now we have to find out n and bn. So that I am doing it here. So n, what is n? 2 over capital T. So 2 over time period is 2. And then on this one, so therefore I did not write the next portion because it will be 0. So just I write these things, ft cosine of n omega naught t. Now omega naught was pi that we calculated. Here you see omega naught was pi. So I got cos n pi t, and then you integrate it from cosine sine pi, it will be sine n pi, and then 1 over n pi, 0 to 1. And then if you put this integral, definitely you know sine 0 means 0, but then when it is 1 sine n pi, as I said here, you look, this thing, sine n pi is 0. Both sine to n pi is 0, sine n pi is 0. So therefore directly you will be applying these things. So that I am doing because it is sine n pi, so that is 0. So ultimately n became 0. Now you have to find out the Vn using this one, ft sine of n omega t. I think that I am doing it here. So Vn 2 over time period 0 to 1, and then see that sine function, and after integrating sine n pi, it will be minus cosine n pi t, and n pi 1 over n pi. So everybody see there is minus sign here, and then I am putting the limit, lower limit, upper limit, 0 to 1. Now here you see this is minus 1 n pi, that is fine. But this one, when you are putting 1, so cos n pi. So therefore cos n pi, therefore look here, everybody this one. Cos n pi is minus 1 to the power n. When it is cos 2 n pi, 2, then it is 1. But when it is simply cos n pi, minus 1 to the power n. So that I said that I have made this trigonometric integral. Everything is available. If you follow this thing, then you are done. So I am putting this thing. So I got cos n pi this one, and then minus, this. If you put t0, then cos 0 means 1. That you all know. Now next step, what I am doing, next line, because there is minus sign here and there is minus sign at the beginning, I am taking this minus here. So first I am writing this one, minus 1 to the power n. Everybody see, I took that minus common. So therefore it became 1, and then minus this term. So therefore that minus and minus, it became plus. Here it is just 1 over n pi. Okay. Now everybody see, because this is n, now n can be, I mean, any value. N can be even number, n can be odd number, right? It can be any value because this is generalized. So that's why I am analyzing here. Everybody see, if you say n is even number, for example, 2, 4, or even 0, then what you are getting, if it is even number, always you will be getting plus on here. So therefore, that 1 minus that one, it will be 0. That's why I said when n is even, this will be 0. On the other hand, look everybody, if n is odd, like 1, 3, 5, always you will be getting minus here, right? So minus 1 to the power 3, it will give you the minus. So therefore minus minus, it will be plus 1. So 1 plus 1, 2. So you will be getting 2 over n pi when n is what? Everybody, could you follow me so far?
Yes.
Yeah. Okay. So therefore look carefully everything. Yes. So therefore I am done. I got Vn is this result. You can say Vn is 2 over n pi, provided that n is odd number. And then before I got, I think a naught was half, and I got n is 0. Now this is your function. In that function, generalized function, you plug in a naught, n, and bn value. Then what you are getting. So therefore, everybody say that function a naught value half that I got, and n value is 0. So I am not writing anything. Just sum n on to infinity bn sine n pi t. Now, what is my the bn? That bn is this one, 2 by n pi. So here what I am writing, that half plus 2 by pi when n value is 1, then sine n pi t, plus then 2 by 3 pi sine 3 pi t. Because when n is odd, then it has this value. Look, when n is odd, it has 2 over n pi bn value that I am putting. If n1, if n3, if n value is 5, accordingly I am writing. So therefore it will go in that way. Everybody, can you follow me this line? So the first one is the generalized function of t, a naught plus n plus bn, that sine and cosine. But we got just a naught half, but a naught 0. So that's why I'm not writing n, directly the bn only, bn sine n pi t. And then this half is this half, and then I am plug in bn value. Everybody look, bn. So this 2 over n pi, that was the bn value when n is odd. That I am putting it here. My limit is n1 to infinity, but I'll be taking n odd only. And then if I do that, what is the bn value? 2 over pi sine n pi t, and then plus 2 over 3 pi, n became 3. So sine 3 pi t, plus when n is 5, when n is 7, it will go in that way. And then from there, you can express it again in similar format instead of writing many terms. You see what I have done, ft on over 2, I have written 2 over 5 and sum k on equal to infinity. I mean, although here I am writing n on to infinity, but n has limitation. What is the limitation? That n can be odd only. N can be odd only, because when n even, then bn is 0. So therefore this thing is applicable when n is odd only. But here I am introducing a new factor, which is k1 to infinity, so that k does not have limit. K goes 1, 2, 3, 4, anything. But then still I have to keep the meaning same. So that's why look this one, 2 over pi sum k1 to infinity. Here I am writing 1 over n. Basically this one, 2 over n pi and sine n pi t, where n is 2k minus 1. Now everybody look, as I said, k value is 1, 2, 3. Let's say k1. So what you are getting? 2 minus 1, n value 1. That makes sense. The n is what? Let's say k value is 2. So 2 is 4 minus 1, 3. N value is 3. That is what, that makes sense, what I did here. Similarly, n is 3. So you are getting, sorry, k value is 3. So you are getting n value is 5. So therefore, I mean, you may or may not write this one. I just wrote on format to represent that so that this summation, properly you can say k1, 2, 3 up to infinity. But then that's why I said, provided that this n value is 2k minus 1. But when you are doing, for example, in exam or homework, and you can leave in this line, no problem. Could you follow me what I am saying?
Yes.
So I
Are
think
you expecting us to change the answer and introduce the summation k to 1
I
and
mean,
doing like that?
no. I mean, I am no. It is not anything mandatory or even not very important. But what I am saying that, for example, our original thing was this one, n on to infinity. This means n can be n1, n2, n3, n4. It is the meaning. But because here we are getting some limitation that when n is what, only then we can apply. So therefore, if you just leave in this format, so you don't know that whether n is 1, 2, 3 or not, because there is limitation. And according to the limitation, for n odd only, I have written these previous lines. That's why here I am writing a generalized format by introducing new parameter k, so that k becomes 1, 2, 3, everything. So this is not any mandatory term, or you may or may not write, that I'm saying. Is this fine? Yeah.
Yes.
Here I am just showing that if you want to say no, I will not be putting any limitation, because here there is limitation. So how can I make it generalized so that k can be 1, 2, 3 for everything? That's why I have written this one. And then this, and then comma, then of course, provided that n here is 2k minus 1. That's why I have put here k instead of n here. So therefore, you may or may not choose this one. Only if you do up to this line, that is fine. Okay, and then I believe you all have done similar things in signals and system or in any math course. So do you remember, everybody, that you have done this type of things? Or
Yeah.
you
In
did
signals.
different thing?
Yeah, I'm not a fan of Fourier.
Okay,
Yeah,
okay,
they're really convoluted.
okay, okay. So therefore here, I will not show many examples, just I showed you one example. In that way, there can be different type of function. Function can be rectangular, so the triangular, or different shape. But then all you can apply this Fourier circuit technique. So therefore, I will not further repeat this, how to apply the Fourier. Now I will show you how you can apply into the circuit problem, this Fourier technique. That I am going to show you from now on. Okay. So now everybody see this one. First look the problem, and then you will be getting. Oh, sorry. Everybody see this one. Let the function ft in figure 1. This is figure 1. I mean, this is the function actually just we did in the previous problem. With a voltage source VST in the circuit of figure 2, then find the response V02 of the circuit. So everybody see, this is your circuit. In this circuit, it says there is a function of Vs. That Vs represent this one. This function has been applied as input to this circuit. If that, then what should be the output voltage V naught across 2 Henry? That is the question. So therefore you see, so far it is simple series circuit. If you know, okay, Vs is this function, there is 10 cosine of omega t, then you can immediately do. You can easily do. We have done a lot of problems in sinusoidal case or the Laplace case. We have done a lot of problems. So circuit is not difficult. Only the challenging here is that you are applying this type of signal here. And then what is the V naught? So therefore, everyone, have you done this type of problem in the signals and systems? Have you applied this Fourier technique?
With circuits.
Yeah, not with an actual network.
Okay, okay.
Yeah, I haven't even taken signals yet.
Oh, okay. So therefore, I think my understanding is that signals and system codes cover up to this type of function and then Fourier analysis. But I think that it does not much cover about the application to circuit. Therefore, everybody look please carefully. That will help you to understand both courses. Okay, so now, now the first of all, so if you see this type of problem, that this is the signal, input signal for this circuit or any circuit, this type of signal, your first task is to apply the Fourier technique. First, you have to convert this on into a sine or cosine form or a DC signal. So therefore, for example, in the previous case, exactly that was the function, for this function, we got, this is the result. Now you see this result has on DC term and then there is sine term. So unless it is sine and cosine term, then we cannot apply any phasor technique. Everybody remember? Phasor technique, phasor algebra technique was applicable only for the sinusoidal function. Or you have learned in DC circuit, if there is DC voltage source, then inductor will be short circuit. If it is capacitor, capacitor will be open circuit. So therefore, unless it is a DC signal or it is sinusoidal signal, you cannot apply easily. So that's why for this type of problem, the very first task is to convert this function into the usable format. So that is, for example, just previous, this is the same example. So therefore, everybody say how I am doing. First, I am saying that what is that VST? The result of this one was this, half plus 2 by pi k1 to infinity 1 over n sine n pi t, where n is 2k minus 1. So therefore, directly I am writing this one because this is the continuation of the previous problem actually, this last term. Okay. Therefore, if I ask you during the exam, or the homework, because if I just say do this thing, then your first task is you have to apply the Fourier, like which is the previous two slides. So therefore, to get this on, like you will spend 15 to 20 minutes, and then you have to start. Therefore, if I ask you during exam, either I will be give you this type of function, okay, this is the input function, or I will just tell you, okay, apply the Fourier technique only. So therefore, in most cases, I will give you the value, this is the function, and then you apply. That I will be doing. Okay, so therefore, everybody see, I got that VST this one. And now what I am writing, omega n, because I want to apply the Fourier technique, what is the omega n value? Where omega naught is fundamental, but for any nth term, what is the omega n? That is n omega naught. And what is omega naught? Omega naught is pi. That we already discussed before. Or omega naught was pi. From there, I am writing that. So this means I got n pi radian per second. Now what I am saying that using phasors, we obtain the response V naught of the circuit by voltage division. You all know it is not difficult to get the voltage. If you have the voltage divided by impedance multiplied by this impedance, right? So first what I am doing, I am converting this circuit into phasor domain. So I just wrote V as 5, this is resistance, this is fine, but 2 Henry is J omega n, right? J omega n. So J L value is 2 and omega n is n pi. This is the generalized format. So J to n pi. So, and then if this is my new circuit, so what is my V naught? That thing I am writing here. Everybody say. So V naught is Vs over the impedance 5 plus J2n by denominator. Here I have written omega n is still, I mean this one. And then J omega n L. So I mean J omega n L is, this is the generalized expression. And then here I am writing that specifically here, or V naught is J omega n value is that n pi. So J2n pi over this one, omega n value 2n pi, and then this Vs. Everybody, could you follow me what I am saying?
Yes.
Yeah. So here, everybody, you have to keep this thing like n, because it is not just fundamental. Because you are applying this signal that has the nth term, nth component. So consequently, you have to, that's why, that is the reason I have written omega n, not just omega naught. Because you don't know that it has only the fundamental or higher order. Definitely there are other frequency terms. So that's why there is n here. Now, everybody see, this is your result, that V naught is this on Vs and this term, Vs multiplied by this thing. So this is fine, you can do that. But everybody now concentrate on Vs. What is Vs? Vs will be this term. Now Vs has two components. One is the DC part, half, and then the next part is this part. So therefore, first everybody look, if Vs is half, if Vs is half, so when Vs is half for DC component, what is the value of the, what is the frequency for DC? DC frequency is 0. So you can say omega n is 0 for DC component, or in other words, n value is 0. So therefore, everybody, if you see, if you put n value is 0, then you are getting V naught is 0. And that makes sense if you really see the circuit. If there is DC voltage applied, then for DC, inductor will be short circuited. So therefore, your voltage will be actually 0. So therefore, directly, whatever the Vs, because this is Vs is half DC, so you can say V naught 0. I have written is inductor acts as short circuit for this. So therefore, either way you go, you think that this is inductor. So for DC it is short, for half voltage it is short, that is also 0. Or in the equation, you assume that your n value is 0. Because this n thing is for like n1, 2, for those fundamental component or higher order component. So therefore you got V naught is 0. Okay, now for the nth harmonic, now there is second term. Everybody see, I mean, this is your equation. V naught is this. So now what is your Vs? This term is your Vs, second term. Everybody, that thing I am writing here. First I am writing, everybody look, my VST is 2 over this one, 2 over n pi and sine n pi t, that I am writing. But because I am applying the phasor, I want to convert sine function into cosine. That everybody look, I am doing this one, 2 over n pi cosine n pi t minus 90 degree. And so that I can write in a phasor format, Vs is 2 over n pi angle minus 90 degree. So now this is my function for this one. So this Vs 2 over n pi minus 90 degree, this represents actually this time domain function. And now you substitute this Vs value into this equation. So everybody see that I'm writing for the nth harmonic, Vs is this one, and then V naught is, now it was 2n pi, so 2n pi, but there are j, so I used 90 degree. And then this Vs is this one, here I am writing multiplied by 2 over n pi minus 90. And in the denominator, I am calculating its magnitude. Everybody say? So root over 5 square plus 2n pi squared, which is 4n square pi square. And what is the angle? Angle is tan inverse 2n pi over 5. You see, this is base and this is in perpendicular. with the j. So tan inverse is perpendicular over base. So this will be your angle. So everybody, could you follow this thing, what I am doing? Are you
Yeah.
able to follow? Yeah. So this means that, I mean, think everybody, this is your Vs function. Once again, I am just repeating, this is your Vs function. I mean, you understood this thing, this circuit, that this is the phasor domain circuit, and your goal is to find out V naught T. So in phasor V naught I am doing, and in the V naught, you have the Vs. So this is the, that algebra format, but this is the Vs. That Vs will come from here. And you are noticing there is half DC term and then that AC term, sine term. So twice you have to consider, and then you have to put it twice. So if Vs value is half, then what V naught? That we got V naught 0. And next time I am applying this one as the input. Then what is my V naught? That I am doing. So that is the thing I was explaining. For this portion, first I wrote here and I converted into cosine so that I can write in a good phasor format. That I did. After doing that, I am substituting this Vs value into this equation. Vs, that I am doing it here. That if you put Vs this on, this is 2 over n pi, and this thing 2 n pi, because there is j, so I am putting 90 degree, and in the denominator, I am calculating its magnitude. Because you see here it is n, so you cannot directly apply in your calculator that what will be the actual value because it is n. So that's why, I mean, from rectangular format, I am trying to put in polar format. That I am doing. So therefore, what is the meaning? Meaning that what is its magnitude? Magnitude is root over 5 square plus 2 square n square pi square. That is the magnitude. And then what is the angle in polar form? Tan inverse 2n pi over 5. So everybody, now could you follow me what I said?
Yes.
Okay. And then you see, you can simplify this one. This is plus 90, but this is minus 90. So plus 90 minus 90, it will be 0. N pi will be cancelled. So in the numerator, there will be only 2 times 4. So therefore 4 over this one. So therefore next slide you see this one. V naught is 4 over that one. And then here you see it was in the denominator, angle tan inverse 2n pi over 5. But if you take it in the numerator, then angle sign will be changed. It will be minus. If you think about when you did phasor algebra, let's say 10 degree. If you take it in the numerator, that is minus 10 degree. That is the meaning. So that's why here minus tan inverse this one. So now this is your result. This is your result. So here you see this was your V naught is this one, but for first component for half we got 0. So therefore, but for the next term, this one we got that one. So ultimately this plus 0 is this one. This is your actual result. Now everybody see, now I am converting into time domain. Think about the phasor algebra. Like you got 10 at an angle of 10 degree. Then what you write? You write 10 cosine of omega t, then a plus or minus angle. The same thing I am writing. In the time domain V naught t, this is that magnitude cosine of n pi t minus that angle. And then sum of k1 to infinity. So why I wrote that one? Because that was my start point, you see, this one. So I wrote this one. And then because it is k1 to n, and then there is n was 2k minus 1. That was my initial proposition, and 2k minus 1. So now I got that one. Now, I mean, you are done. You are done here. Just I am showing few values. You may not need to do this. The first three terms, if you put k1, 2, 3 in this equation, or n value 1, 3, 5. If you put k1, 2, 3, you will be getting in 1, 3, 5. If you put n 1, 3, 5, and then if you calculate, then you will be getting some result that v02, this thing will give you 0.498 on. And then for n value 3, you will be getting this on, and n value 5, you will be getting this term. Just I'm showing you that what type of result you will be getting if you really put n value 135 or k value 123. But I mean, you can leave the answer here. Everybody, could you follow?
Yes.
Yeah. I mean, it looks like a little bit difficult, but actually it is not difficult. I mean, everybody, once again, you think in that way. I think you will be go next class. You think in that way. Let's summarize. I mean, in every circuit problems, in case of Fourier series, there will be a function. In this case, this is function, but it can be rectangular, triangle, or other sinusoidal format. First, you have to convert into Fourier series. Therefore, in this case, like I have given, this is the result based on the previous knowledge of the previous problem. Now you will be looking this thing, you will be looking what is the circuit, what it is asking. In this case, it was asking the voltage here. So easily you see that it is voltage division. If you know how much current is flowing, then that current multiplied by this one. That you did first on. And then your input has two terms, one DC term and one this term, nth harmonic term. So therefore, or there can be three terms, for example. Therefore, for each term, you have to find out what is your V0. That is the thing I was doing. Therefore, first I consider, okay, if that value is input value is half DC, then what? Next time I consider, if this is my input here, then how much? And then finally I summed up, and then I got this is my V0 in phasor form. From the phasor form, I converted into time domain format. So that's the result. And here I am just showing you the some result. What should be this value V0 value if k is 1, 2, 3, or in other words, if n is 1, 3, 5. So that's why if you have the calculator, you can see you will be for first three terms, you will be getting these things. So is everybody clear? Or is like still you are facing some difficulty?
I just need more practice.
Yes.
Yes, it'll be rough.
Yeah. No, I understand. That's why I'm repeating. So, and as I said, that you might not have applied this type of technique in that signal systems course. So therefore, what I'll be doing, you see that these slides are already uploaded on eCourseware, class lecture 29, and again, soon I'll be uploading my video. You can see what I would recommend everybody please again after the class, or when you have free time today, you look this on, you look line by line, and you try to understand, then it will be fine. And in next class, I will be showing you another 2 to 3 different example, not this one, different example, different circuit. Then it will be clear to you that how to apply that thing into the circuit problem.
Hey, Doc, it looks like your class 29 notes are messed up.
Oh,
Like they don't have all those trigonometric integrals and identities, and it's like incomplete.
oh really? Yeah. But exactly I uploaded these slides there.
If you download it, it fixes it.
Okay.
Oh, probably you are looking that view topic from there directly, right? Yeah.
Yes.
So therefore, as that's it, probably you need to download and then it might appear. But I'll be checking also that what is wrong, it is going on there. But exactly these things are there. Exactly. Anyway, so everybody please try to understand. I think first part you all understand, right? That Fourier circuit technique. I mean, how to find those constant. I think up to that, up to this thing, it is fine. Everybody will look this on. That when I am applying this technique into the circuit problem, you all understand this calculation, then you will be fine. And I will show you more example in next class and other class, so then everything will be clear to you. Okay, so with that, I think some of you have next class, so please you proceed to the next class. Do you have any questions, comments?